Good day. We are going to present BEV 20203 Transform Circuit project titled Comprehensive Analysis and Simulation of Non-Sinusoidal Transient and Steady State Response in Linear RLC Circuits via Fourier Series Decomposition by Group 9 Section 4. Introduced to our group members Liu Zibing, Ethan Zhong, and me, Wen Jiaquan.
Hi, I'm Ethan, and this is our chosen input waveform in the circuit. So, the amplitude for our input voltage is 3, the VPP is 6, the VP is 3, and then the frequency is 1 over 6. And for our circuit, we have the voltage input and the resistor, capacitor, and the inductor all in parallel. And the inductance is 2 Henry, capacitor is 1 farad, and then the resistor is 1 kilo ohm.
Hi everyone, my name is Liu Zibin, address number AE240041. So today I will talk about the manipulation for our based on the waveform for the chosen input waveform, which is an odd symmetry waveform. So as we know that an odd symmetry waveform has no an value and also a not value. This we have already verified at our report, but however at here I will just talk about the Bn value. Okay, so first of all, we need to identify the amplitude. So from 0 second to 3 second t, it is 3, positive 3. From 3 to 6 t, it's negative 3. So this is the amplitude. And based on this, we can find out the omega naught. So omega naught is equals to 2 pi over t, and it is equals to pi over 3. So now, based on this information, we can find the Bn. So the Bn, the formula is Bn is equals to 2 over t, uh, integration from 0 to t ft sine n omega naught t dt. So we can substitute all the value inside as we know already. So the Bn value for the first part from 0 to 3 is equals to 2 over 6 integration from 0 to 3 3 sine n pi over 3 t dt plus 2 over 6 from 3 to 6 negative 3 sine n pi over 3 dt. So we are going to integrate this by using substitution method. So after we substitute with the integrate, we will get the 3 over n pi bracket negative 3 n pi over 3 t. So we are going to solve for 3 and 0 and minus 3 over n pi negative cos n pi over 3 t bracket 6 and 3. So based on this, we know that when n equals to 1 is equals to 12 over pi. When we input as n equals to 2, you get 0 value. So in conclusion, we can know that the Bn value for odd value, which is the n equals to 1357, is 12 over n pi. For the even value, for even n, it is 2468 is 0. So in conclusion, for the Fourier series, it is equals to the sum of n equals to 1 to infinity 12 over n pi sine n pi over 3t with a condition of n equals to 2k equals to 1. Yep. So for the expanded Fourier series, for the first one, the bottom one, sine pi over 3t is the first value, and plus 1 over 3 sine pi over t is the third value, and 1 over 5 sine bracket 5 over 3 pi t is the fifth value, and so on and so on. Yeah. Okay, continue for the manipulation for circuit analysis. For our group, we are using an RCL parallel circuit, which all the components are parallel to the input voltage source. So since the input source is parallel with the resistor, capacitor, inductor, the voltage for the input source is equals to have the same value as each component, including the resistor, capacitor, and inductor. So next we are changing the Fourier series the into from S domain to from T domain, time domain to S domain. So we get 4 over S squared minus n pi over 3 bracket square. So by changing back to time domain, because all the components have the same voltage, we get back the same value, which is 12 over n pi sine n pi over 3t volt. So for current for resistor, we are calculating using basic Ohm's law, which is IR over VR over R. So for IR, we will get IRT, we will get 12 over 1000 m pi sine m pi over 3t. By substituting a condition n equals to 1, t equals to 1, we will get IR is equals to 3.31 times 10 to the power negative 3 ampere. So for calculating a power, the resistor is the only component that has real power as it dissipates power, and for the inductor and capacitor has only the reactive power as its stored energy. So the resistor power we are calculating using the power formula, which is the VRMS squared over R. So when n equals to 1, substitute into the voltage, the voltage 12 over n pi sine n pi over 3, we change to 12 pi sine pi over 3t. So 12 pi over 3 is the is the amplitude, the maximum amplitude for the voltage. So for calculating a VRMS is 12 over pi square root 2. Okay, and the resistor is the resistance is 1000 ohm. So by putting all the value inside, we will get 7.3 times 10 to the power of negative 3 volt. So at here, I will only show the current for the resistor and current for resistor, because we will discuss for the current for inductor and capacitor later at the discussion part. Okay, thank you.
So this is our software simulation, and at the left side we have the input part, and then this is the waveform of our input voltage. So after the input voltage, we have the resistor, and then the capacitor, and then the inductor. So below the resistor is the emitter. It shows the current of the branch, and then this is for the middle one is for the capacitor current, and then the right side is the current for the inductor. And then at the most right part, there is a node voltage for the upper node. And then since we only have two nodes in this circuit, and the bottom node is connected to ground, the bottom node is 0. And then at the K here, we can see at the right side of the resistor here is the power for the resistor, uh, which shows 0.007411. That is the power for the resistor.
Here, we compare our manual calculations against the MATLAB simulation. As shown in the table, the power of resistor show a very strong correlation. The manual calculation gave us 7.30 milliwatts, while the simulation gave us 7.41 milliwatts. This is a percentage error of only 1.48%, which proves our fundamental frequency calculation was highly accurate. However, we will notice that the current has a higher error of 10.3%. This is not a calculation failure, but rather a limitation of the simulation display. The simulation output rounded the reading to 0.003 amperes, which lost some precision compared to our exact manual calculation of 3.31 milliamperes. To conclude, our group successfully achieved the objective of analyzing a linear RLC circuit using the systematic mathematical techniques. We proved that the Fourier series is an essential tool. It allowed us to transform a complex square wave into a manageable sinusoidal component. Our findings also highlight an important trade-off. While manual analysis requires us to truncate a series, usually focusing on the fundamental frequency, it provides a solid mathematical understanding. In contrast, the simulation captures the cumulative effect of higher harmonics, giving us the complete picture. Ultimately, the lower percentage error in power confirms that the Fourier decomposition is a reliable method for determining the steady-state response of linear circuits. That is all for our presentation. Thank you.